In previous lessons, we've examined flow control valves that regulate the flow rate of hydraulic fluid in a system, and we've discussed directional control valves, which determine the path of hydraulic fluid in a system. In this lesson, we're going to look at pressure control valves. These valves are used to control the fluid pressure in various parts of a hydraulic system. A pressure control valve is either normally passing or normally non-passing, sometimes referred to as simply passing or non-passing, depending on the position of the spool in its normal non-actuated state. The valve will change from passing to non-passing or from non-passing to passing with changes in pressure at the valve. Pressure changes are sensed in two ways: directly through an internal pilot passage in the valve itself, or remotely through a pilot passage that extends to some other part of the system. As we will see, some valves have both direct and remote pilot passages which can change the state of the valve. First, let's take a close look at valves that sense pressure directly. Most of them are normally non-passing, like this one, a pressure relief valve. The passage through the valve from the primary or inlet port to the secondary or outlet port is normally non-passing, so it remains closed until pilot pressure at the primary port overcomes the force exerted by an adjustable spring biasing the valve spool. When that happens, the spool shifts and the valve opens. Typically, a relief valve is used to limit the pressure in the system by allowing fluid to return to tank when system pressure exceeds the setting on the relief valve. Normally non-passing pressure control valves can also be used as sequence valves to make sure one operation occurs before another. For example, suppose a drilling operation involves clamping a workpiece with one cylinder, then feeding a spinning drill bit into the work with another cylinder. A sequence valve can do this. Shifting a directional control valve sends fluid to the clamping cylinder and toward the drilling cylinder. The sequence valve installed ahead of the drilling cylinder stops the flow because the pressure isn't high enough to overcome the force of the spring that keeps the valve non-passing. Once the clamping cylinder reaches the end of its stroke, system pressure rises, eventually overcoming the force of the spring in the sequence valve. When the valve opens, fluid flows to the cylinder that moves the drill bit into the workpiece. A normally non-passing pressure control valve can also be used as a counterbalance valve in a hydraulic circuit. For example, a counterbalance valve is often used to control the movement of the platen on a press. Dies bolted to the heavy platen form metal parts as the platen is pressed into a workpiece. Platens often weigh several thousand pounds, and they must always be mechanically blocked whenever they are not being used. Never rely on a valve to hold a platen in place. Without a counterbalance, the piston rod in the cylinder holding the platen would run out uncontrollably as soon as flow is directed to the cap end of the cylinder. To maintain control of piston movement throughout the downward stroke, a normally non-passing pressure control valve is installed downstream of the cylinder. The valve is set high enough so it won't open until pressure at the valve inlet port is higher than the pressure caused by the weight of the platen alone. The pressure at which the valve will open and the platen will descend can be controlled by the setting on the valve. Three factors are important for the correct operation of pressure control valves: cracking pressure, fluid temperature, and pump wear. Each may require adjustments to pressure control valves in order to maintain proper operation of the system. The pressure at which a normally non-passing pressure control valve begins to open, the cracking pressure, is less than the rated pressure of the valve. For example, if a relief valve is adjusted to open at 1,000 psi, that doesn't mean the valve will suddenly open at that pressure. Actually, it will start to open before that, probably somewhere around 800 psi or less. As pressure climbs toward 1,000 psi, the valve opens farther, and more of the pump flow goes to tank. By the time system pressure has reached 1,000 psi, the valve has opened up to its rated flow. Flow through the valve changes as pressure rises from cracking pressure to full rated pressure. Therefore, the cracking pressure of a relief valve must be taken into account when a particular flow rate is important to the proper operation of a system. For example, the relief valve in this system is set to open at 1,000 psi. The pump develops 750 psi to deliver a flow of 10 GPM to the cylinder. 550 psi is needed to move the load, and another 200 psi is needed to overcome the resistance of the fluid in the system. As long as the system pressure remains below the relief valve's cracking pressure of 800 psi, the system works well. But if the resistance of the load increases, let's say to 700 psi, then the pump has to develop 900 psi, 700 psi for the load and 200 for the fluid resistance. The 900 psi might open the relief valve about halfway, allowing 5 GPM to return to tank. If that happens, the cylinder will fill much more slowly, and rod velocity will be substantially reduced. The second factor that affects the performance of normally non-passing pressure control valves is fluid temperature. We learned in an earlier lesson that as the temperature of a fluid increases, its viscosity or thickness decreases. The thinner a fluid, the less pressure is required to push it past a restriction. If the fluid is cold, the viscosity will be higher, and the system will require greater pressure to reach a specific flow rate. Pressure control valves are usually set while the system is at normal operating temperatures, even though this causes the system to develop higher pressure at startup when the fluid is cold. Setting pressure control valves at startup will cause system pressure to drop as the fluid warms up to normal operating temperature. Finally, wear on the pump can also affect the performance of pressure control valves. As pumps wear, they become less efficient. Gradually, flow output decreases and system pressure declines. A gradual decline in flow and pressure over time may be an indication that the pump requires repair or replacement. Now, all the pressure control valves we've seen so far have been normally non-passing valves which sense pressure directly. There are also some types of normally passing valves which sense pressure directly. These are called pressure-reducing valves. A pressure-reducing valve works by responding to pressure changes at the secondary port rather than the primary port. When pressure through an internal pilot passage exceeds the spring pressure on the spool moves, restricting flow through the valve and reducing pressure on the secondary side. If pressure drops, the spring pushes the spool back, increasing the pressure. During normal system operation, the spool balances at an intermediate point and maintains a constant pressure on the secondary side of the valve. A pressure-reducing valve is often used to adjust the force which actuators produce. In this circuit, cylinder A is supposed to clamp an object with a fluid pressure of 1,000 psi, and cylinder B must clamp with half that pressure. Instead of installing a smaller cylinder at B, we can use a pressure-reducing valve to bring the pressure down to 500 psi. Once pressure at cylinder B reaches 500 psi, the pressure-reducing valve closes. However, pressure continues to rise at cylinder A until system pressure reaches the setting on the pressure relief valve, 1,000 psi. Pressure at cylinder B remains at 500 psi. Flow rate affects the performance of a pressure-reducing valve. For example, if a valve is set to reduce pressure from 1,000 psi to 800 psi at a certain flow rate, increasing the flow rate will reduce the pressure even further, below 800 psi. This decrease in pressure in a pressure-reducing valve is called droop. This graph shows how droop increases as flow rate increases. Droop is also more pronounced at higher pressure settings. For example, notice how much more droop occurs at 1,000 psi than at 500 psi. Pressure-reducing valves may have to be adjusted if flow or pressure change. All pressure control valves use some fluid for lubrication, but as a valve wears out over time, fluid leaks past the spool into the spring chamber. Excess fluid in the spring chamber will interfere with normal operation and must be drained. Many drains are internal. That means they empty into the secondary port. This works well for relief valves and other valves with secondary ports that return to tank at low pressure. However, the secondary ports on pressure-reducing valves and sequence valves contain fluid at working pressure. Trying to drain the spring chamber into the secondary port in this case would prevent the spool from shifting properly. In these situations, the spring chamber must be drained through a separate or external line. External drains are indicated on the symbol with a dotted line from the spring area to a tank symbol. Internal drains are not schematically illustrated. If the symbol does not include this dotted line to tank, the valve is internally drained. Now, we've seen how pressure control valves sense pressure internally through a passage within the valve body, either from the primary passage, like a relief valve, or from the secondary passage, like a pressure-reducing valve. This type of pressure sensing is referred to as direct sensing or direct operation. Pressure can also be sensed in some other part of the system by means of an external line. This is called remote sensing or remote operation. Counterbalance valves, like the one we saw earlier, are sometimes remotely operated. For example, in this hydraulic press circuit, a pilot line senses pressure upstream of the cylinder. This allows us to maximize the force which can be applied as the platen presses through the workpiece. Let's take a simplified circuit and see how it works by assigning some values to the circuit we saw earlier. Suppose the platen weighs 5,000 pounds. One side of the piston has an area of 20 square inches, and the rod side of the piston has an area of 10 square inches. The weight of the platen, 5,000 pounds, creates a pressure of 500 psi. That's 5,000 pounds divided by 10 square inches. If our counterbalance valve is set for 550 psi, nothing moves, because the pressure created by the weight of the platen alone is not quite enough to open the valve. However, as soon as the system generates an additional 50 psi in the rod end of the cylinder, the valve opens and the platen goes down. Now, suppose the system's relief valve is set for 1,000 psi. As the platen presses into the work, the downward force is 1,000 psi times 20 square inches, or 20,000 pounds. When we add the weight of the platen, we have a total of 25,000 pounds of downward force. However, with the counterbalance valve set at 550 psi, fluid in the rod end of the cylinder exerts a pressure of 550 psi on the 10 square inch area of the rod side of the piston. This pressure is commonly called back pressure. In this case, it means we are losing 5,500 pounds of force. So instead of having 25,000 pounds pressing on the work, we only have 19,500. But if we want the weight of the platen to help do useful work, we can operate the valve remotely by installing a pilot line to the upstream side or cap end of the piston. With the counterbalance valve set for a low pressure, 100 psi for example, then as soon as the pressure on the upstream side of the piston is 100 psi or more, the counterbalance valve will open and the platen will descend. When the pressure falls below 100 psi, for instance if the weight of the platen tries to pull the piston away from the pump flow, the valve closes and the piston stops abruptly. When the system is operating and the platen descends to the work, the pressure rises to 1,000 psi, resulting in 20,000 pounds of downward force, just as before. This time, however, the platen adds its 5,000 pounds for a total force of 25,000 pounds. As long as pressure upstream of the cylinder holds the counterbalance valve open, back pressure is eliminated and all the force is downward. Counterbalance valves are also used with hydraulic motor circuits to apply back pressure to the motor to control the momentum of the spinning load. This is commonly done with a brake valve. A brake valve is operated both directly and remotely. It has an adjustable spring which biases a spool that controls flow between the primary and secondary ports. The spool can be moved either by a separate piston that responds to internal pilot pressure at the valve, or by pressure applied to the spool by a remote pilot line that senses pressure just upstream of the motor. In this circuit, the tension on the bias spring has been set so the valve will operate at 800 psi. If the pump stops while the motor is turning its load, pressure will fall below 800 psi and the valve would close, applying back pressure at the motor outlet port to break the load. In our example, the cross-sectional area of the spool is 8 times greater than the area of the piston, so only 1/8 as much pressure is required to move the spool. Commonly, remote pilot pressure of 100 psi at the motor inlet is enough to open up the brake valve. As long as pressure at the inlet to the motor is 100 psi or more, the brake valve will remain open. If the load attempts to run away, pressure drops off in the motor inlet line and the valve closes. When that happens, back pressure rises and slows the load down. The valve does not reopen until back pressure reaches 800 psi or until pressure at the motor inlet returns to 100 psi as the motor and its load stabilize. Now, all pressure control valves, except relief valves and unloading valves, must be able to allow reverse flow back through the valve. Since normally non-passing pressure control valves sense pressure at the primary passage, as soon as flow is reversed, pressure in the primary passage is reduced. The valve closes. Flow from the primary passage to the secondary passage is blocked. That means we have to direct flow around the pressure control valve by using a check valve. The same technique is necessary for normally passing valves like pressure-reducing valves. Even though they sense pressure at their secondary port and might continue to pass fluid under reverse flow, any rise in pressure could close the valve. Therefore, check valves are used with normally passing valves as well. Very often, these check valves are included in the same housing as the pressure control valve. In this lesson, we have seen several types of valves used to control pressure in hydraulic systems. In the next lesson, we'll take a closer look at one of these, the pilot-operated pressure control valve.